So, hello everyone, this is Animesh Das, and this I'm presenting my video report on project on project 2 of Science-1. That is the theme is double pendulum, and here goes. So, this is what the double pendulum looks like, and we are to look at the dynamics of this double pendulum. So, let the double pendulum have two strings of length L1 and L2 and two pendulum balls of mass M1 and M2. M1 and M2 please. And let these angles be theta 1 and theta 2 with respect to the y axis. Now the coordinates of the pendulum balls will be x1, y1, x2 and y2, which we have calculated. The velocities of the pendulum balls can then be found out by differentiating these coordinates with respect to time, which gives us some function of theta 1 and theta 1 dot, theta 2 and theta 2 dot. Now, using these, you find the kinetic energy as follows, the potential energy as follows. The Lagrangian can then be found out as Ls equals Ks minus Us, which is this big expression here. Now, hold on a second, and there you go. The state coordinate, as you have observed there, the each of each of these expressions depends on theta 1, theta 2, theta 1 dot and theta 2 dot. That is they vary with these angles given given m1 l1 and l1. They vary with these parameters. Now, so these are what will define your system state. Now, for the given system, the this Lagrangian equation is applicable because there is no force F naught or something like, or anything of that sort on the system. Now you find now all we need to find is the partial differential of this Lagrangian with respect to each of the coordinates, and use these two equations, calculating calculate the LHS of the these two equations to find that these two these two conditions are applicable. So these give you, so as you can see here, if theta 1, theta 2, theta 1 dot and theta 2 dot were constant, this would have been the case. These and these would have been variable, right? So for every theta 1, theta 2, theta 1 dot and theta 2 dot, this is what you'll get. Okay, now this, and where alpha 1, alpha 2, f1 and f2 are functions of the state coordinates, and this is how you, and these are the functions as found. Now you see f1 and f2 don't depend on theta 1 and theta 2 respectively, surprisingly. Now that ensures that we can make this matrix here, and this matrix has some value, right? So what does this mean? We can write this as a system of linear equations in two variables, that is system of two equations in two variables, two linear equations. Now you see this coefficient matrix of our system of linear equations is invertible. How? 1 minus alpha 1 alpha 2 is greater than 0 no matter what, because alpha 1 alpha 2 is less than 1 no matter what. Now, well, it's not going to be equal to 0. Even if it's negative, it would have been, it would have worked. So since a is invertible, a inverse, since the determinant is non-zero, so a inverse exists, so a is invertible. Therefore we can write theta 1 dot this row matrix as this, which finally gives us the evolution of theta 1, theta 2, omega 1 and omega 2 has this. So now that we've looked at the derivation of the dynamics of the double pendulum, let's look at how it would look like when it is simulated. The simulation will be run for 10 seconds. Okay, 10 seconds is too long, I guess. Um, but I guess you guys get the idea, right? I guess stopping it requires a lot of patience. So yeah, I hope this video was enlightening enough. So thank thank you for have thank you for your patient watch and have a good day.